Hello, everyone. This is chapter 16, lecture 19 and 20. And so, what I wanted to do first is go over moment of inertia. I mentioned it briefly in some of the lectures, but let's just go over it real quick. Now, this is going to be a add-on lecture to the one I'm posting. It's of similar material that I covered in a lecture back in 2023, and it's essentially the same. So I'm not going to repeat it all because I'm going to post that lecture also. But just to give you kind of a overview, we know that the mass moment of inertia, if you go back to chapter 9.5 and look in that section, it discusses the relationship between mass and inertia. And inertia is going to be an important part as we talk about rigid body rotation, especially in this chapter and in chapter 17. So effectively, the mass moment of inertia is very similar to the area moment of inertia. The difference being is that now you have a term that's usually referred to as mr squared, as you can see on the screen. Now, in the other video, I did go into more detail on this, so I'm not going to repeat that here. I would encourage you to watch that video first and then come back and look at this one. In that video, I went through the the units. This is primarily the important part of this slide. We're not really going to deal with three-dimensional moment of inertia, so our moment of inertia will be fairly simple. And we did do this example. We went through this example of how to find the moment of inertia of a composite object, very similar to what you would do or did in statics to find one. Really no difference there. We went through also this example. Two pendulums, A and B, with masses of length shown, are released from rest. Which system has a larger mass moment of inertia about its pivot? And so we can see that the one with more mass is going to have that. And so we can compare that to the two if we look at, let me show that here. If you have the two links, one like this and one like that, and this on this end has 2m and this end has just m, then if you think about the way we do I equals mr squared, then really for this one, it's going to be what? It's going to be 2m, and this will be L over 2. This will be L, so it's L over 2 squared, which is essentially 2m L over 4, or just ml over 2, right? Whereas in this one, we have what? ml squared. So we can see that if you compare the two, that the longer object is going to have the larger I. And this is, remember from statics, that when we had I equals whatever the one, let's say it's a rectangle, 1/12 bh cubed, and then we always added to it an AD squared. That represented the area that was away from that center of rotation. And of course, the farther you get, the more inertia or resistance to rotation that you have. Okay, so that says that, and it's not something that we're going to derive first each time. We'll have a table of values for it, and oftentimes we'll use this relationship of the radius of gyration, which says that k equals the square root of I over m. Or you can write that as k squared times m equals I. Okay, so this will be coming back to in some of the problems that we'll do. Now, in the other video, I did go over this material here, and if I stop sharing, let me give you that again, that stuff's in the other video, but let me give you kind of an overview again of that. Now, remember what we're saying is that if you have an object, here's your center of gravity, and you have a bunch of forces acting on it, that though that object we can write as equal to is if we had a mass times acceleration of the center of gravity and a rotation denoted as I bar alpha. Okay. Now, I derived that in the other one, but it comes down to, if you recall from statics, you have a moment, right? So if you think of back in statics, that if this was my point of my moment, MO, that's my R, that's my force. Then if that's my center there, O, then what would I have? Actually, let me draw it this way. So we have our force out here. We have R there. We know that R cross F is our moment. So we learned that in statics. Okay. So now we have to take this and we have to look at the other aspect, which is the angular momentum. Now, in angular momentum, we have kind of a similar situation, that if we have a three-dimensional momentum, let's just say we have this vector mv. There's and we know mv is just linear momentum, denoted as L, linear. And then what we do is we say, well, what's the difference between linear and angular momentum? Well, angular momentum we call the moment of momentum. And if we wanted to know what it was, we would draw a vector from there to there, call that R, and we would know that our H, which is angular, would be equal to R cross mv. Okay? So that's just the distance crossed with the linear momentum, and that's all it is. And in a scalar sense, we can write it as H equals mvr. Okay. Now, if I take the time derivative of this, so I take d dt, then what do I get? I get that's equal to the d dt of H gives me r dot crossed with mv plus r crossed with mv dot. Okay. And again, I'm just taking the time derivative, and you take the ddt of this term here, you end up with this and this. Now, this velocity and r are the same thing. So this is basically velocity crossed mv. Well, if these are, as we've drawn them up here, they're in the same direction. So it'd be like saying I crossed with I, or J crossed with J. That's equal to 0. So this term actually disappears. And what we're left with is R cross MV. Well, what is that? That's R cross MA, because V dot is A. So what does that look like? Looks a lot like this up here, doesn't it? So effectively what we're saying is that if we want to, we can say that the change in linear momentum about the center of gravity is simply equal to R cross MA, okay? Or HG equals the sum of the moments about G. And that's it. That's really the main point that we'll be using. We'll use it over and over again, but we'll come back to it. All right. Now, another thing I want to talk about before I do examples is the idea of linear momentum. So if we take again linear momentum, we know it's just mv, angular momentum hg, and again g being the center of gravity. Okay. So we have our hg, and we know that that equals r cross mv, right? Now, in the book, it talks about summations, and that's fine. That I would look that over too to see how it's derived. But kind of in a nutshell, what we get is R cross omega cross R times mass. And that's really because what is velocity? We know that velocity we can write as omega cross r. We learned that in chapter 15. So when the smoke clears, what this really reduces to is hg equals the omega times mr squared. And so I've skipped a few steps, but that's effectively what it is. So the book and in the first lecture goes into more detail. But so what does that equal to? Well, we know that is equivalent to I. So what it says is that the the angular momentum about G can be written as I times omega. Sorry, getting ahead of myself. I omega. Okay. And if we take the time derivative of that, hg dot, or the change, so this is the change in angular momentum, right? Well, then that's going to equal I alpha, right? So there's radians per second squared. But remember that we already said that h dot g equaled the sum of the moments about g. So now what we can say is the sum of the moments about g equals I alpha. Okay. Now, another part to this is that's all well and good if you're at the center of gravity, right? So that's G. But let's say that you take the moment about a different point. So let's say draw a point up there. We'll call that point P. Okay. So now our moment's about that instead about this. So now we say the sum of the moments about P equals I alpha, but it's going to be plus MAD perpendicular. Now, what this comes from is this is saying that D perpendicular is this distance R here, okay? And we know that acceleration equals R alpha, right? Just like omega equals, um, I'm sorry, just like velocity equals r omega. The accelerations are alpha. So if we say d perpendicular is equal to r, and we substitute this in, we get I alpha plus m r alpha r. Or if we simplify, it becomes I plus m r squared all times alpha. And so what I've said is if I take the moment about a point other than center of gravity, then this is really just the parallaxis theorem, right? I plus mr squared times that. So it really hasn't changed any. We've just kind of written it a little different and rearranged the equation. Okay. So that's really chapter 16 in a nutshell. Now, again, I know just reading and seeing me go through this is still going to leave you with a lot of questions. So at this point, I want to go through a few examples, and I think those will help solidify it. And of course, when we meet back in class, I can answer questions and we can go over a few more examples. Okay, so here's an example. Let's just look at the example. We have a door on a hinge, and the hinge slides forward. We assume there's no friction. We're given that the weight is 200 pounds, and we want to determine two things: how far the door goes if pushed from rest for 2 seconds at a force of 30 pounds, and that's more just a simple F equals ma. But the part that's pertinent to this chapter is finding the vertical reactions at the rollers A and B. So pause this, write it down. This problem is also on the course notes for last week, which should have extended to Friday. So take a look, and now let's go ahead and try to solve it. So here we have our object, force, normal force A, normal force B. Now they point up because the wheels on this are kind of like a barn door. You can think of the wheels there like this, and then they kind of hang over. So the force is upward. The wheels are the weight of the door is hanging down, so the normal force is up. Now, from a practical standpoint, if you think about this, if you push the door hard fast enough, then it's going to want to rotate about A, and effectively B will, if you rotate it fast enough, it'll go to the point where the whole object starts to physically turn. So it starts to have angular acceleration. Now, in this case, it's not going to, because we're not going to have any angular acceleration, but what we're going to have is a reduction of force on B due to that rotational or that acceleration. So let me show you. So first, you start off with the free body diagram. There's P, there's our mg, and of course we have our na and nb, okay? And then that just equals this max, and that's at the center of gravity, okay? Now, uh, one of the things about in this chapter too, and again, that's why it's good to read it and go over the information I post, is the way to think about the acceleration is that you have this relationship we call it the sum of the moments about, in this case, we're going to take it about A equals the sum of the moments about A effective. Now, what this is saying is it's saying, first off, what are the sum of the moments about A? Um, so we can figure that out. Some of the most A effective are essentially what moment is created by the acceleration of the center of gravity. So this is a very important point. So you might want to pause it and write it down. So again, what moment is created by the acceleration of the center of gravity? Okay. So before we write that down, let's first figure out what the acceleration is. Now, we know that it's 30 pounds. That's our force. So F equals ma, right? So I have, so F equals ma. So we have 30 equals 200 over 32.2 for the mass times A of G. So not too hard. So acceleration, the center of gravity is 4.83 feet per second squared. So if we want to know how far it goes in 2 seconds, it's just delta S equals what? 1/2 A t squared. So if we substitute in this for that and 2 for that, then we quickly have our answer. So that didn't do this problem to do that because that's really easy. So 9.66 feet is how far it goes in 2 seconds. So that's chapter 12 stuff. So now let's look at this finding NA and NB. Now, in a static example, NA and NB, since they're symmetrical about they're both 6 feet from the center, then we would just say they're each 100 pounds. But, and that's fine in statics, but for dynamics, as you push this way, there's a tendency for this door to want to rotate. So it wants to effectively rotate like this up. So what that does is it puts less load on B and more on A. So what we're going to find is that the normal force on B is actually going to be less than it is on A. But no matter what the distribution is, these two forces still have to add to the total weight of 200. All right. So let's look at what I was saying about the sum of the force moments about A, sum of the moments about A effective. So if we do that, we have the normal force of B times 12, right? And this is counterclockwise. So normal force of B, 12 feet away from A. Again, we're summing the moments about A, okay? And then we have minus the weight, that's 6 feet away. So that's just your mg right here at a distance of 6. And then plus 30 times 9, right? Because it's a 12-foot tall door. And so we know that if that's 3 feet, this has to be 9 feet. All right. And that's counterclockwise also. So we have all of that. Okay. And then on the other side, we look at what is the MA effective. So what is the moment created by the acceleration of G? So really, we write it as MA D perpendicular, right? That's what it's looking at. So, and I'll roll this back to the in a second. So we have M8, that's basically what, so we have the mass again, 200 over 32.2 times 4.83 feet per second squared, right? Because that was the acceleration that we found. And then this distance is the perpendicular distance. So let's think about that. If this is my door, then the perpendicular distance of G, if G is here, going that way, then that's this here, which since we're told that it's um, 12 feet high, that means that the distance perpendicular has to be 7, right? Because this is told 5 feet off the ground, so that's 7. So it's 7 feet. So 7. Okay. So now we just plug in the numbers. We're looking for NB. We know the weight. We know 30, so we can solve. And we get normal force B equal to 95.0 pounds. So therefore, normal force A has to be 105.0 pounds. Okay. So, you're probably asking where'd the original equation go? Well, let's look at it. So remember we said the sum of the moments about G equal I alpha. But we're not using about G. We're doing the sum of the moments about P, some fictitious point that's not the center of gravity. And that equals what? I alpha plus MAD perpendicular. So what happened to this term? Well, there is no angular acceleration, right? There's G wants to cause a moment, but the physical object here is not moving, it's not accelerating. And that can be kind of weird, but think about it. The only way that this would accelerate is if you pushed it hard enough so that the normal force at A was less than 0, because then that would mean that the load was completely off this and now it's starting to move. So that's how to think about it. It's kind of the same idea as like a wheelie in a motorcycle. And that's what we're going to do next as an example. Go back. Okay. So here we have a four-wheeler. Okay. And our four-wheeler, similar to uh, it could be a motorcycle, whatever. But so we have this thing, we're given the weights. So I would take a second to write down these details and draw the drawing. And even if you think, if after the past example, if you think you could solve it, that would be good too. So I would say pause the video now, try to solve it or get as far as you can, and then look at it. This will go a long way to helping you. Go ahead, pause it. Okay, you're back. You paused. You worked it all out. Now you know the answer. That's good. Let's go over it. So gonna stop there and let's draw out what we have. Let me pause this next so you have to watch that. Okay, here's my drawing. Um, Now it might help to have the picture that I posted next to it, but so I have the wheels, normal force A, normal force B, friction, mass of the motorcycle. It's not really a motorcycle, but I just use M, and then mass of the rider. So that's where their locations are. So the distances that are important are 2 feet, 1 foot, 2 foot based on. So the 2 foot represents where the center of gravity of the ATV is, and the um, the 1 foot up here is where the center of gravity is at. So down here, it turns out that the center of gravity isn't as important this way as it is this way. So what I've drawn is this is the center of this is the acceleration down here of the ATV. It's 1 foot off the ground, and the acceleration of the rider is up here at 3 feet off the ground. So think of it as you accelerate, the back wheel starts to skid, and the question is, what is um, what is the maximum acceleration that you can do so that you don't end up or how I guess if you read it, it's a little different than the past problem because it wants to know how much acceleration can you apply and how much friction coefficient do you need. So we're looking at this point from the friction end, but it's still the same concept. So, for example, we're going to sum the moments about B. Now, the reason we're going to sum the moments about B is because that's going to get rid of the normal force B and the friction force mu static NB, since we don't know those. So we take the moment about B, that eliminates them. Now, we're assuming that NA is 0, which means that we want to know what is the maximum friction so that we can cause it to just start to wheelie, but not wheelie. So by this being approximately 0, we're saying that the sum of the moment about B equals I alpha plus MAD perpendicular. Now, we're saying that is 0 because we're constraining it to say there's not going to be any angular acceleration. So we just have to worry about this. So what that reduces it to is sum of the moment about B equals sum about the moment B effective, where again, this is the moment created by the acceleration of the center of gravity. Okay. So the last one was very simple. We just plugged in the acceleration center of gravity and the moments here, and we found one variable. This is a little different because in this case, we're looking for the friction coefficient, but we still started out the same way. So we'll go ahead. Sum of the moments about B equals sum of the moments about B effective. And so we have what? We have 335 pounds, and that's 3 feet, right? So we have 335 pounds, that's this here, and it's 3 feet away, right? And it's counterclockwise with B. So of 335 times 3 plus the rider, 150 pounds, and he or she's only 2 feet, so 2. And then that's it. That's all the moments we have, or all the, and so that's going to equal then the total mass 335, sorry, over 32.2, the mass times the acceleration. And then what's the distance? The distance is 1, right? And that means that's this distance down here. Okay. Well, we don't know the acceleration yet. So then we're going to do the same thing. We're going to say 150 over 32.2. And this acceleration, of course, has to be the same. So it's going to be A, and then it's going to be times 3 feet this time. Okay. So the fact that, so we're saying if NA is 0, then our acceleration turns out to be about 53.5 feet per second squared. So now think about that practically. That's 32.2 is a G. So this is like a 1/3 of a G. And if you've ever ridden ATV or motorcycle, you don't accelerate that fast. That's more like a roller coaster or maybe a drag car if you're in that. Um, so but so we want to do is see you know, is that a realistic value? And well, what can the writer do to kind of change that or in order to be able to move accordingly. So how big does the friction have to be, is the question. So go ahead, come back to our chapter 12 stuff. We know that if we sum the forces in the y to 0, then we get what? The normal force of B minus the weight of the man or woman minus the weight of the the weight of the actual motorcycle, which I'm calling, and then the weight of the rider equals 0. So basically, it's just the sum of all that. So our normal force at B, all the weight we're saying is concentrated at the back, 485 pounds. So all the weight is there. Um, and then if we look at summing the forces in the X, then what do we have? We have mu times, and that's making this way positive. We have mu static times the normal force, 485, right? That's basically mu static times the normal force. And then that equals what? Ma. So the mass times acceleration. So in that case, it's going to be what? It's going to be 335 over 32.2 plus 150, and put that all over 32.2, and then multiply that by 53.53 feet per second squared. So if we solve that, sorry, it's a little sloppy. That's the weight, 335 plus 150 all over that, because you can combine them to have the same acceleration, times 53.53, the full value, and then divide that by 45, and you get a friction coefficient equal to 1.66. So remember, the original question, as it was asked, was determine the largest coefficient so that the rider won't tip, or won't leave the ground. So the only way that the wheel will not spin, just basically sit there and burn out, is if you have a friction coefficient of 1.66. So then the question asks, well, what would require in order for that to change? Well, essentially the rider would have to crouch lower. Now, even if, so for example, if the rider crouched to 1 foot, so when you think about it, the rider's up here at 3 feet, now they're suddenly down to center of gravity. So basically, I don't know how that's even physically possible, but even if they crouched to 1 foot, then it would still, uh, the coefficient of friction, I'm sorry, the acceleration that it could handle would be 62.1. So it's the question is really more of a qualitative one. It says, in order to increase acceleration, should the rider go straight up or down? Well, they obviously should go down, because that's going to lower the moment created by their center of gravity. That's the important takeaway here. And it turns out that if we had a coefficient of friction of just 0.3, which is a more realistic in dirt and mud, then they can only accelerate at about 4.94 feet per second, which is a lot more realistic. So parts of this question were kind of silly, but the main part I wanted to convey was, how do you deal with this? Some of the moments about B, some of the moments about B effective. And I think after you practice a few, it should make a lot more sense. All right. Hopefully that's making more sense now. Do another example. Okay. Here's another example. Now, maybe I should have done that one before the last one, but let's look at it. Now, this one is this is kind of a pure application of that equation I told you about. So here we have a flywheel. Let's just, I would say, take a moment to either screenshot or take a picture or write down what this looks like. Flywheel has a radius of 20 inches. It weighs 250 pounds. It has a radius generation of 15 inches. Now you have a 30-pound block at A is attached to a wire that is wrapped around the flywheel, and you release it from rest. So neglecting the effect of friction, determine the acceleration of the block and the speed of the block after it has moved 5 feet. So finding the velocity will be very easy. That's just basic kinematics. So let's find the acceleration, okay? Using the same thing we just talked about, right? So if you want to try it on your own, by all means do so. If you can understand it, you're that much better off. So, okay, well, let's go ahead and solve it. All right, so here's what it looks like. Now, we have the actual wheel, okay? Now, I've written the radius is 20 inches. The weight of the flywheel is 250 pounds, okay? Uh, the mass that we're given, again, was 30 pounds. And so what we want to do is, sorry, I'm just, yeah, 30 pounds. Sorry, I just want to make sure I got that right. So what we want to do is, as before, first we'll look at our free body diagram. We know that at the center in B, you have a weight, and then oftentimes they'll draw a BX and BY as the reactions. And I see this in a lot of diagrams, even though we don't care about them. It's just something to note. So, we have our weight here. So that's going to be, of course, 30 pounds. All right. Now release it from rest. So again, we're going to take the moment about B. Now, again, that's not the center of gravity because we have this weight out here. And even if it was, we still have an external weight attached. So the way to think about it is we're going to sum the moments about B, and we're going to make clockwise positive, equals, again, the sum of the moments about B effective. Okay. And that's going to be equal to, well, first off, what moment about B is even created? So that's what you have to look at. Well, the only moment that's created about that center is the weight. So we have the mass of B times G times the radius of B. All right, that's it. And then that is going to equal I times I of G. So when I say IG here, I'm saying the moment of inertia of the flywheel, right? Because that always has to be I of G, and that's going to be times alpha plus MAD perpendicular. Okay. So that's my sum of my moment about there. So let's expand it a little bit. So moment about B times G times RB, and that equals IG. Now in this case, what I'm going to do is I'm going to substitute because I know alpha is equal to acceleration over R, right? Remember, acceleration is R alpha, so I can substitute that for A over R, okay? And then I can also say plus M A R, right? Because my D perpendicular is R. It's just that distance. It's the, if you think about it, here's the acceleration, there's the R distance, and there is the acceleration down, causing it to rotate. Okay. You don't put the MAD on this diagram. In fact, this diagram only has the I alpha on it. Now, in this case, we actually have angular acceleration, so that doesn't drop out, unlike the previous two problems that we did. Now, another thing to note is we are given that the radius of gyration, K, equaled 15 inches. Okay. So that's nice because, and I'll erase this and I need more room. Because remember what I said is that if you want to know the moment of inertia and all you have is K, then I equals K squared times the mass. So in this case, I is going to equal. Now, one of the things we have to remember too is that we're dealing, as long as we're dealing in pounds, we have to convert to feet because gravity, if we convert this to mass, gravity's in feet per second squared. So our I is K. Well, if K is 15, it's really 15 over 12 as far as feet go. So it'd be 15 twelfths, 15 over 12, give us it in feet squared. And then the mass of the wheel is 250 divided by 32.2. Okay. So when the smoke clears, I equals, and usually we designate as I bar meaning about the center of gravity. It's going to be 12.13. And remember the units, pound, feet, second squared. Okay. So there's I. And then, of course, R, we have to convert that to feet. So that's 20 over 12, which gives us 1.667 feet. Okay. And our mass of A, is equal to 0.9317 pound second squared per foot. So that's basically 30 over 32.2, right? So that's our mass. So again, English units, a little more cumbersome, but as long as you're consistent, always make things in feet, always divide by gravity to get your mass, then you're okay. So now we have everything. We can bring it over to here, and we know MBG is just 30 pounds. So we have 30 pounds, and then times the distance, 1.667. And then that equals IG, which I found. That's going to be my 12.13. And that's going to be 12.3 pound feet second squared. And then I'll divide that by R, which was 1.667 feet, right? Because that's the radius. And then I'll move A out here. Okay. So feet cancel. And I end up with pound second squared. And then that's going to be plus what? My mass. So 0.9317. And that's pound second squared per foot. I'm just kind of putting the units in here to show you how they work every so often. And then we have times A. Sorry, it's getting a little messy. Put this down here. So it's not 0.9137, that's my mass, times A, which I don't know, and then times R again, which is what? It's 1.667, and that's foot. So again, feet cancel. So my units are consistently pound over second squared. All right. And then over here, you'll notice that this foot here is here and pound is there. So the point is that I want units ultimately to be in uh, feet per second squared, which is what they would be because the second squared and the pound would be divided and the feet would stay here. So I'd end up with um, this ends up being 50 pound feet when you multiply it equals 7.22. I'm sorry, not 2227, 7.2778 pound second squared times A plus 1.5529 pound second squared times A. Okay. So you can see that if I divide, I'll end up with the pounds all cancel, and my units end up feet per second squared. So it would have worked out fine, but just every so often it's good to go back because, again, if the units don't work, then obviously there's a mistake somewhere. So I end up with 50 pound feet all divided by 8.8307 pound second squared. And so acceleration is given as 5.66 feet per second squared. Okay. So again, there we have it using this substitution. Now the substitution I erased, the acceleration equals r alpha. That works as long as there's no slipping. As soon as you're slipping, then it's all out. But fortunately, in our class, very rarely are we going to have slipping. Most of the time, we can use this A equals R alpha. Okay. So the velocity at 5 feet would just be v squared equals v naught squared plus 2a delta x. So that's just going to be what? 2 times 5.66 times 5. And so we get 7.52 feet per second. Oh, and that's all square rooted. Okay. And that's it, because that's 0. So hopefully that helps a little more. That's what I had planned to go over a Friday and part of Monday. And so the next lecture will cover 16.2, which is an extension of this. And it's very similar in the way you solve it. So I think, and then when we get into the last part of it, then that will be kind of the culmination of chapter 15 with the stuff we learned in chapter 16. All right. So thank you for listening, and I hope this made sense, and I'll see you in class. Take care.